Alright guys, so in this session we will continue with the linear quadratic regulator and trying to obtain the closed form solution for it. So the last time we obtained an equation that needs to be satisfied at the solution, at the optimal solution. Okay, so we have 2a x squared of t plus 2b x of t u of t dt, an integral over all time plus x0 square is equal to 0. So this needs to be satisfied at the solution, optimal solution. Okay, so now we will try to combine this with our objective function. Okay, so let us multiply both sides of this by let us multiply both sides by a finite constant with p, a finite constant, okay. So we have this thing becoming p times 0 to infinity 2a x squared of t plus 2b x of t u of t dt plus p times x0 square still being equal to 0. Okay, so since this whole thing is equal to 0 at the optimal solution, okay, if we add this whole thing to our objective function, we do not change the optimal cost value. Okay, so we can add this term to our objective function. Okay, so because at the solution this term becomes 0, therefore at the solution it doesn't have any effect on our cost function. So remember that our cost function, which is a function of u of t, was composed of a first term, which was a combination of the state and the input. So this is our original objective function, but what we are saying is that we can add this the entire above term to this and do not affect the value of the cost function at the solution. Okay, so 2pa x squared of t, so I'm distributing the constant p inside of those expressions, so plus 2pb x of t u of t dt plus px0 square, okay, is our cost function. So let us try to keep manipulating this in order to combine the terms. For example, we can put everything inside the integral. So we have r u squared of t plus 2pb x of t u of t plus qx squared of t plus 2pa x squared of t dt plus px0 square. Okay, So let us continue with this regrouping. Our aim here is to make the cost function or put the cost function in such a form that it's going to be fairly obvious what the minimum value should be and when we can achieve the minimum value. Okay, and the typical way to do that is to put everything into a kind of a square form, okay, or a quadratic form, where you know that everything's going to be positive, and then the minimum value is achieved when if you can make certain terms zero. Okay, so let me continue with this. So I'm taking this into R parentheses. So I'm going to have to divide the second term by R because it doesn't have any R term. So 2pb over R x of t u of t plus q plus 2pa x square of t. So we also take it into x square of t parentheses dt plus px0 square. Okay. Now this term we want to kind of what we call complete into a full square. So complete into a full square. So what we will try to do is to, let's call this term as alpha. Okay, so what we are trying to do is make u squared plus 2 alpha. Hold on, I have a phone call. Okay, so we are completing this into a square. So that means a form that is u squared plus 2 alpha x 2 alpha xu, and because this corresponds to the form here, we also need to add and subtract the term that's going to complete the expression into a full square. Okay, so that means this becomes u plus alpha, so something square, and minus another term here, alpha square x square. Okay, so this is the full square term. Okay, so if we apply this to our cost function, what we get is the integral still r times parentheses. Here we have the full square. That means u of t plus pb over r x of t squared. Also, we have this term that needs to be added, in fact subtracted, in order to match the expressions. Okay, plus the term over here, right, q plus 2p pa plus x square of t. The integral is completed, plus px0 square. Okay. So now let's deal with the, let's take this term and move it to the second part of the expression. Okay, so we have the first term plus pb over r x of t squared. And then, so let's finish this integral here and divide it into two parts, where the second integral becomes minus p square b square over r square x square of t, and plus q plus 2pa x square of t dt plus px0 square. Okay, now we see that x square of t is a common factor here. So the expression, the first part is the same, u of t plus and the second integral becomes basically q plus 2pa minus p square b square over r square times x square of t dt plus p x0 squared. Okay. So we spent quite a bit of time, but we have put our objective function into a form that we can actually draw some conclusions on. Okay. Now remember that p is a finite constant, but it's not determined. Basically, it is free. So now we can choose p. Okay. We can choose p in order to try to minimize this cost function. Okay, and the best way to choose p, if we can, is to basically make this term 0. Okay, can we make this 0? Okay, now in order to do this, we need to solve this equation equated to 0. So if there is a solution, p equals p star, that is the solution of this equation, q plus 2p star a minus p star square b square over r square. Okay, so p star here, that is equal to 0. Okay, so we want to find p star in order to make this term equal to 0. Okay, now as we will see, this is not a simple task. Okay, but that is why this equation has a special name. It's called the algebraic Riccati equation. Algebraic Riccati equation. Okay, now you see that if we have everything being a scalar, obviously this is a quadratic equation that I can solve p star for. Okay, but if it's in the general case, as we will see, this becomes a vector matrix equation, and it becomes a bit in fact much harder to solve. Okay, but can be solved in some special cases. Okay, so if we do this, and this makes the second term here vanish. Okay, the cost function j u of t in that case becomes only the first term plus this term at the end, the constant term at the end. So this is going to become r times u of t plus p star b over r x of t square dt plus p star x0 square. Okay, now this whole thing is the minimum cost possible if we can solve the algebraic Riccati equation. Okay, under p is equal to p star solution. Now we have another question. Okay, how can we also minimize the remaining part? Okay, can we also minimize the remaining part? And the answer is yes, because take a look at this term. Okay, we can u of t is our input. that we are trying to find. Okay, so in order to minimize the function, we can also deal with this part and try to make that equal to 0. Okay, so by the way, this algebraic Riccati equation is often shortcut with ARE. So the answer is yes, and we can achieve that by choosing the input essentially being equal to minus P star B over R x of t. Okay. That choice of the input actually makes this term, okay, makes this term also 0. And we can do that because we are free to choose U. And note that what we are doing here, the particular choice of UT, is in fact a state feedback, in fact a negative state feedback. So this is our optimal U, okay, and U star of t in this case is equal to minus k times x of t. Why? Because P star is the solution of the algebraic Riccati equation. It's fixed. B is fixed, R is fixed. Therefore, U star of t becomes a constant minus a constant times x of t and is a linear state feedback. Okay. So, in fact, what we have found as the solution of the optimal control problem, the linear quadratic regulator problem, and we have obtained nothing but a specific state feedback controller. So the solution of the linear quadratic regulator problem this is our LQR problem, is a linear state feedback controller. Remember when we had discussed the state feedback in 302, okay, basically the way we use the feedback controller is that we specified the locations of the closed loop poles, and then we use the pole placement algorithm in order to find the linear state feedback matrix K. Okay, so what we are effectively saying now is that in the LQR controller design, you don't explicitly specify the pole locations, but the optimization problem that we solve actually determines the pole locations for us, and also it gives us the proper linear state feedback that we will implement, okay, which is given by this equation that we have obtained. Okay, so let me break the video here, and I'm going to continue over the same PDF file, okay, but with a new video.